Welcome back to the series of lectures on high-performance scientific computing. One of the things that we constantly deal with high-performance scientific computing is putting out large amounts of data. Because we do these extremely large-scale computations, it inevitably results in extremely large data sets. Now, how do we sort of make sense of this large-scale data? One of the best ways to do it is to visualize this data in different formats. But visualizing large data sets itself is a challenge which we need to undertake. Nowadays, especially with the advent of machine learning and AI, we are getting even more larger sets of data, and sort of efficiently mapping them and representing them is very important. So today we will look at some scientific visualization, or the process of taking this data and trying to make sense or represent it in a human readable format. So what is a scientific visualization essentially? It is a process of where you're taking the scientific data and mapping it into a set of images. At the very basic level, you can think of it as a graph plot, which we all have learned in our schools, where we take X and Y data and represent it as a line plot. We can take percentage data and represent it as a pie chart, or we can show bar graphs. Now, it is evident that humans will understand information in an image much better than we just understand it by just looking at a bunch of numbers. So, effectively, what we are trying to do is trying to convert the raw data that has been created into information and then thereon into knowledge. So, visualization effectively represents the scientific data to the human visual and cognitive system, which is then used for analysis and interpretation. So, why do we need this analysis? Obviously, we want to extract, communicate this knowledge and insight. We also want to explore and understand this data, sometimes interactively examine this data, looking for aspects of the data which might be interesting. This is when we are working with the data by ourselves. Finally, we need to communicate this data to our communities, to our peers, within the research group sometimes, or to an external community via presentations, publications, and scientific papers. So for this, scientific visualization is very necessary. In scientific visualization, we typically deal with data that represents some sort of natural phenomena or has some sort of natural spatial structure. Though this is not necessary, we could also look at some abstract data like financial markets. So we could look at medical data, which is usually measured using some sort of MRI or magnetic resonance imaging or CT scans. We can look at geospatial data, which is either computed or is measured from actual satellites or other instrumentation. Engineering data, again, which is computed through simulations or measured on the field. Chemistry, biological data, which can either be computed and measured again. So when we are trying to explore this data, it requires a very interactive visualization. So we need to generate images almost in a real time. And as you know, human beings have very limited tolerance for delay. So good graphics is actually necessary. Imagine if you're trying to watch a movie and the movie frames are extremely jerky and you do not see the smooth transition in these movies. It can get quite annoying. Similarly, when I'm doing scientific visualization, I want to see nice animations which have very little jerk and smoothly transition from one form to another form. Similarly, when I'm analyzing the data, if I'm doing any cuts or if I'm doing any sort of modifications to the data, I want to have as less delay as possible. And we need good graphics hardware for that. So to aid this data visualization, there are many modern visualization packages. And they all use something what is called as the pipelined component based architecture, which we will discuss a little bit in detail. These modern visualization packages, to name a few, ParaView, MayaVi, Visit, Avizo, so on and so forth, they all take advantage of some universal formats. So effectively what the users can do is quickly assemble this modular software components into some sort of finished application. Because each user will have a different way of representing a data. For example, a medical doctor would like to represent the MRI scan of a brain in a certain way, whereas a geospatial engineer would like to map, say, for example, the flood basin of a river and demonstrate it in another way. And each of these have different final visualizations, but they all start with very similar raw data. In the sense, this data is represented in some sort of spatial and temporal numbers. So what you really need to do is take these components and combine them in a different ways to get to a certain visualization level. And that's what the researcher does. And these software need to be extremely flexible. These software all come with pre-existing tools with which you can take your raw data and transform it to the desired visualization that you need. But sometimes these features might not be available. It also needs to be extensible so that if I want to add a certain feature, I should be able to program it in so that I can add new components to the system, hence extending the system's functionality. So we will now discuss one of the most popular visualization tools, ParaView, which is a project which started in 2000. It was started by a company called Kitware and also the Los Alamos National Laboratory. This is an open source software which is continuously supported by Kitware, and it contributes to the ParaView development. ParaView is built on top of something called as the Visualization Toolkit. The Visualization Toolkit is sort of an open standard for how to output scientific data, and this toolkit came out of GE research. The first public release of ParaView was in October 2002, and as of now, we have had several new releases of ParaView. You can go to this below link to actually check out ParaView. So what does ParaView actually do? ParaView provides a full set of tools for manipulating, transforming, processing, rendering, and also animating this data. It allows for visualization and analysis based on points, lines, areas, volumes, images, or geometric primitives in any particular combination. It is not limited to what sort of primitive shapes that you use. So it's not limited to, say, structured graphs or any particular shapes. It can take any arbitrary shapes and generate images. It also provides a powerful parallel execution and advanced display, which is for 3D stereoscopic viewing. Why do we need parallel execution, and why is there para in the title of ParaView? Remember, generating this image itself can become a computationally very heavy task, because we are taking this raw data and we are transforming it in such a way that we want to display it on a regular two-dimensional display. So we want to take a 3D image and sort of project it on a two-dimensional display, plus we have a whole bunch of other calculations and modifications that we want to run on it. So these calculations can become tremendously expensive to render the final image that is viewed by the user. Again, the user might also want to dynamically interact with this view, like changing the view immediately, holding and dragging, so on and so forth. So the rendering has to be sort of done on a pretty much immediate basis. And hence, if you have extremely large data sets, then it might be necessary for the rendering itself to be done in parallel, because the data set could be quite large. So how does the ParaView software architecture look? The ParaView uses what is essentially a client-server model. In the standalone mode, where you're using ParaView on your workstation or desktop or laptop, the client does all the processing on the local machine. But sometimes the data could be large enough, and your laptop or your desktop or your workstation might not be powerful enough to process all this large amount of data which is being put out by HPC. Then in that case, you can split the client and the server. The client is where actually you're sitting and interacting with the data. It always runs on the workstation, or it's basically the graphical user interface. You then have a server in the background. The server is remote from the client at this point of time. It could be a single process on a local or a more powerful remote machine. It could be multiple processors like on a distributed shared memory machine. And the server can process the split data into data servers and render servers separately as well. The server does all the computation at this point of time, and the client just puts up the final display. So think about it. If I have to render an image, the actual calculation of the image of how the projection should look is being computed by a different, more powerful server, or even a set of compute nodes on a distributed architecture. And then only the final image is being relayed to the client, and the client is now seeing it on his or her desktop. So this is how the visualization of the ParaView architecture will look. You'll have the data server, which has n components and has data parallelism. It'll go and read sections of the data. Let's say that you have a very, very large data set over here. It's going to read different bits of the data. It's going to communicate with each other on MPI. And then the data is then going to be manipulated by whatever manipulations that you would like in terms of transforming it to the view that you would particularly like. Once those transformations are done, they're then given to the render server. The render server then actually creates the image which needs to be displayed on the monitor, and then this is finally given to the client. Both the data server and the render server are separate and can run with multiple instances on multiple nodes completely in parallel, whereas the client will typically run on a single workstation because it is the final display that needs to be shown. So you have the data server, which will take loads of data, process each of it in parallel, take strips of data, do whatever calculations is required, pass it on to the render server, which itself can run in parallel to create the composite image. And then once the composite image is created, it sends the composite image to the client, and then the client will then sort of display it on the monitor. So think about this like this tile display. So each render server will probably make a display for each of the tiles and then send it over, and then the client sort of assembles it and then puts it out on each of these tiles. So this is typically how the ParaView interface looks. This is for a calculation that we did. We have loaded some data over here. So you have the different toolbars over here which allow you to open, close, save files. It allows you to connect to the different data servers, the render servers over here. And then it allows you to perform certain operations on this side. You can take filters, something like contours, you can take clips, you can take slices of planes, you can take selections, threshold of surfaces, you can create glyphs, you can create streamlines, so on and so forth. Essentially what happens is that you take in the raw data and you load it over here, and once the raw data is loaded, it will give you a representation. The raw data is then processed. In this case, it has been processed with a contour, and the contour basically shows the ocean depth in the Indian Ocean. And you can see the red parts essentially are showing the deep parts of the ocean, the green parts slightly shallower, and the blue the absolute shallowest near the coast. And it takes the raw data in the form of X, Y, and Z, Z being the depth, and then colors it in this contour over here. You can then now look at it in terms of the object inspector, and you can look what's really going on with this data. You can see, you can even draw contours and saying that I have drawn a contour of roughly 3,600 meters. You can see the depths of where 3,600 meters is, and you can see these contour lines over here. You can create multiple contours, you can create multiple filters right over here. You can take this data and process it as a series of filters. So what we need to think of any visualization is in terms of a pipeline or in terms of a data flow. The data flows from the source, which is a reader, which is usually a raw text file. It reads in the file and then sort of displays it. And then the data is modified or manipulated by filters. And then it is transformed and mapped into a geometry, and then finally the geometry is rendered onto the screen. So to go back, so you can see the actual data is for this particular thing is stored in an X, Y, Z format, where X and Y are the lat and longitude locations, Y is the depth of the ocean over there. Then this data is being read and then being geometrically rendered in this manner, and then we then go ahead and produce the colors to look at the contour levels. So the data travels between these operators, and you can make many modifications and many filters with it, right? So data is a source which is providing the data for the visualization system. Usually it's written in a file. It can come directly from your program as well. A filter then takes this data from the source, manipulates it in some way, passes it on. You can do things like selecting the data of interest. You can transform it, you can scale it, you can threshold it. You can then take the mapper and takes this data and creates geometric primitives which then can be rendered. Something like points, lines, polygons, or colors. For example, I can take this data of the Indian Ocean and threshold it and say, please show me points only which have depth greater than 3000 meters, and then all the other points would vanish off. Or I can say, please show me only points which are 100 kilometers away from the coast of India, and it will take away all the other points. So you can create different filters like this by defining the mathematical attributes, and then the actual render will take place. So the visualization pipeline works somewhat like this. You can take the source, which is the raw data, then apply different filters to it. It could be any one of these filters. You could put multiple filters, like one filter over the next one, or filters in parallel. Then finally you put the mapper, and then you find the put the renderer. So this is how the visualization pipeline works completely in all. Now, ParaView has support for many techniques for generating renderable objects. So it can take data in the form of points, and it can put scalar data, points, and as in glyphs. It can generate contours and isosurfaces. It can put histograms. It can even generate 2-dimensional and 3-dimensional plots. So let's say if you want to see the variation of, say, temperature at a particular latitude from that case which I showed you, or the variation of ocean depth at a particular latitude, you can get 2-dimensional plots. For vector data, you can look at arrow plots, you can look at streamlines, so on and so forth. The visualizations also need to be annotated, in the sense, for example, in the case of the Indian Ocean. Now, we are very familiar with the Indian subcontinent, so we sort of readily recognize this image. But it's quite possible that some viewer or some student might not be familiar with this map. So we can annotate this, saying that, oh, this is the west coast of India, this is the east coast of India. We can add text to this plot and give the appropriate legend. Now, this is the case for geospatial data. Now, you could look at any other scientific data where labeling would be sort of really necessary, because for the layperson, most of this data might not be very obvious. So you can add ribbons, tubes, axes, text. You can display data locations, you can put the meshes, you can put the boundaries. We can also interact with the data. For example, if I want to probe a particular point, let's say that I'm looking at fluid flow through a pipe, and I want to look at the velocity at a particular point or at a particular line segment, I can actually probe, and I can select a location in the volume and see what the conservative variables are at that particular point. I can also pick a location on the surface of an object. I can do arbitrary surface and volume sampling, saying that I can pick an arbitrary surface within the pipe or an arbitrary volume within the pipe. I can do cutting, I can map planes, I can look at cut sections, so on and so forth with ParaView very easily. So ParaView is built, as we said, with the visualization toolkit, and it understands the visualization toolkit's data formats. There are 5 types of classic formats which are old but now very common. One is structured points, which go in Cartesian structures. Then there is structured grid, there is rectilinear grid, there is unstructured grid, and there is polydata. All of these files will have the extension .vtk. The visualization toolkit also understands the VTK XML data formats. So you can output data in several formats, and it will take in all these data and then make the appropriate calculations and render the image. ParaView also can import many common scientific file types. The thing is, you could be using some commercial software, or you could be using some other proprietary format or other open source formats. So for example, it will take all the VTK file extensions, which are sort of exhaustively listed here. It will take the ParaView specific extension .pvd. You have other self-describing data formats, which are popular with high performance computing, which is HDF5 and NetCDF. This can be read in directly by ParaView as well. You have the insight.case and .sos files. If you're looking at biological work, protein data banks PDB files, chemistry work like XMOL and Gaussian cube files, ocean files for ocean simulations like .pop, direct images like PNG, .tif, and raw binary files. Apart from this, if you're still putting out data in your own custom format, you can program a custom reader for reading in your own data. This is one of the beauties of ParaView, that where you can add code in bits of Python to read data in your own format, or make a modification or a filter which is non-existent in ParaView but you would like and to make that transformation. Thank you.